Hello, I'm Reem, and I'll present our work, Doppler volume rendering. To begin with, I think we're all more familiar with Doppler effect when it happens to sound waves. For example, when a car is approaching you in the road, its pitch goes like and this is Doppler effect. Doppler effect can also happen in light waves. However, instead of being perceived as a change in the pitch, it's perceived as a change in the color. When a source is moving in a certain direction, the waves in that direction are compressed, causing a blue shift in the spectrum. Similarly, the waves here are stretched, causing a red shift. Although they are called red and blue shift, they are rarely visible to the human eye. The naming just denotes the direction in which the spectrum shifts to. The reason why they are not visible is because Doppler effect depends on the ratio between the moving object divided by the speed of light. And everything in our daily life is significantly slower than that. And this is why Doppler effect shines when dealing with data of extreme physical magnitudes, such as stars and galaxies that move at hundreds of kilometers per second. Astrophysicists routinely do 3D simulations like the evolution of galaxies or the merging of black holes, and they need to physically visualize those with Doppler effect taken into account. And so, our goal is to, in real time, apply Doppler effect to volumetric data of galaxies. The main contribution of this paper are, to the best of our knowledge, we are the first accurate Doppler effect computation in volume rendering. We also adapted spectral volume rendering with two different emission models, the line emission model and the blackbody emission model. And we proposed a novel piecewise linear representation that overcomes the traditional drawbacks of the point-sampled solution. And of course, we also implemented this in the GPU. As an overview of our system, in a nutshell, we aim to visualize Doppler effect applied to volumetric data in real time. To do this, a volumetric galaxy dataset is taken as an input, which contains the star densities and the information necessary to get the spectrum. In addition, a velocity field is essential for the Doppler computation. Then, we're going to take this data and visualize it using spectral volume rendering while applying Doppler effect to the spectrum using the given velocity field. It's worth noting that the spectra is represented using our proposed piecewise linear spectrum representation. Spectral volume rendering is basically an extension of the traditional volume rendering. However, instead of accumulating RGBA values, we work with the spectrum directly throughout the rendering process. And then every volume element can emit or absorb light at any frequency. And then once we exit the volume, we just convert the spectrum into an RGB color. It has many advantages for our purposes. For instance, it offers realistic optical effects and a physical correct representation of the spectrum. In addition, the transparency now depends on the wavelength and not on the alpha channel, like the traditional volume rendering. We can deal with electromagnetic emission outside of the visible range, such as infrared or ultraviolet. In terms of the spectra and astrophysical data, light radiance comes from the matter both as thermal radiation or by photon generation. Thermal sources are modeled using an idealized black body. In physics, an idealized black body is a source that emits radiation based on its temperature and doesn't absorb anything. To compute the spectrum of a black body, Planck's law is used, and as you can see, it only needs the temperature at a given point to calculate the black body intensity. The figure here, for example, shows black body model at the spectrum of the black body model at different temperatures. Our sun, for example, can be modeled by a black body at temperature around 5,500 kelvins. And you can see that the peak moves to the left as the temperature increases. That's why the color goes from red to blue as the temperature goes up. The other model is photon generation by free charged particle acceleration. Different materials absorb and emit light differently due to the chemical nature of their components. For example, this is the hydrogen emission lines and this is the carbon emission lines. And while they are shown like delta peak they never occur like this in nature due to the different broadening effects, such as pressure or thermal broadening. Now, we have the emission model that will give us the spectrum, and we have the galaxy density and the velocity field that will be used to calculate Doppler effect. And we are going to pass all of this into the spectral volume rendering, giving us the final output that we want. It's now time to talk about how this is done and how the spectra is represented. The classical way of representing the spectra will be to bin it using the point sampled spectral model. For example, this emission lines will be mapped into this bin solution. And then at every step along the ray, we are going to sample the density, and we will sample the velocity field and then cast it into the ray, the direction of the viewing ray. And then we'll apply Doppler effect to the spectrum, giving us our shifted spectrum. For example, this was redshifted, and the intensities are scaled accordingly. And we are going to get a spectrum like this at every step along the ray, and then we're just going to add them up due to the spectral additive nature. And once we exit the volume, we convert the final spectrum into an RGB color. However, this model has some limitations. For instance, it could over or underestimate the Doppler effect. If the spectral line was shifted but it fell into the same bin, it will be underestimated. On the other hand, if it was shifted slightly but fell into the next bin, it's going to be overestimated. In addition, we have a loss of energy conservation. Although the spectrum looks like this, we have unwanted peaks here because two spectral lines fell into the same bin. We can also have unwanted absorption line, and we can also lose information of the bins that fall out of the bin range that we have. And all of this depends on the number of bins. For example, if we used 400 bins to represent the spectrum, we get 3 lines here, but if we used 40 bins, they're all merged into one bin. This is why we propose a piecewise linear spectral model that overcomes those drawbacks. In this model, we model the spectra as a bunch of linear pieces, a bunch of non-overlapping linear pieces over a certain interval. What we are going to do at every step is we are going to take 2 samples, apply Doppler effect, giving us a trapezoidal shape, and then we'll do this for every line in the spectrum, giving us this spectrum. And we are going to get something like this at every step along the ray. But now those accumulations are not as easy as just adding them up anymore, because now we have lines instead of bins. And for accumulation and for lines, we have around 11 cases of how they should be added on top of one another. In short, the piece will be broken down at the overlapping point, and the overlapping region will have their slope and intercept summed up, giving us a new piece. And this will continue until no overlapping pieces are left. And as you can see, it's a very recursive process, and it's expected to be the most time-consuming part of this algorithm. Now, once we get the final spectrum, we are going to convert it into an RGB color. However, we can't do this directly. We have to convert it first into an XYZ color, and then just do the trivial linear mapping between XYZ and RGB. To do the spectrum to XYZ color mapping, we model the CIE functions as linear pieces as well, and then convolute it with our piecewise spectrum. Since both are linear pieces, we can just do the simple math to give us an easy-to-implement equation in our renderer to get the XYZ color. In terms of the implementation, our code was run in the PC with Intel processor and 128 gigabytes of RAM running Ubuntu OS. The graphic cards was NVIDIA Titan RTX with 24 gigabytes of memory, and all of this was written in C++ using Coda 10 and OpenGL 4.6. We used the Sormani dataset, which simulates the asymmetrices in the innermost region of the Milky Way, and we resampled it into a uniform grid of size 128. You can see here the black body density, the hydrogen density, the carbon densities, and of course the underlying velocity field. Here's how the dataset looked in our renderer. For the black body, for example, we have its density and the temperature. And for the different materials such as hydrogen, we have the hydrogen density in addition to the hydrogen emission and absorption lines, and of course, the underlying velocity field. For our results, we show the photon generation results without Doppler effect. And this is the spectrum at the selected point. And once we apply Doppler effect, we can see the redshift in the spectrum. We can also see a point that was blue shifted. Secondly, we show the results of the black body emission, and we can see how the peak moves to the left or to the right, depending on whether it was approaching or getting further from the observer. Lastly, we can apply both at the same time, and we can look at how the spectrum looks like when we apply Doppler effect. In all cases, we can see the spectral accumulation along the ray and how the spectrum changed until getting the final spectrum. You can see here that the lines kept accumulating for 163 steps along the viewing ray. To compare our solution to the point sampled solution, we notice that the point sampled one has a higher energy due to the bending issue discussed earlier, and the resulting image reflects this as well. In comparison, our model is more accurate, and you can see the trapezoidal shapes as well. We test this more accurate claim by showing that increasing the number of samples in the spectrum makes the resulting image converge to the one produced by our method, but it requires a much higher rendering time. Now, to optimize our method, we implemented a merging mechanism. When two neighboring lines have close slope and intercept, they are merged into one piece. This improves the performance and reduces the space needed to store the spectrum at the cost of the accuracy. For instance, by increasing the tolerance, the number of pieces goes from more than 1,000 to 100 pieces, but the resulting image is more noisy. However, this is needed when there are so many emission lines, the renderer isn't able to store them all in the GPU anymore. Looking at the performance, we recorded the rendering time both for no Doppler effect and with Doppler effect. And here we show the spectrum at the selected point in both cases. For black body, the rendering time was optimal. But for line emission, it really depends on the number of lines in the model. For example, when we do hydrogen, which has the fewest emission lines, it takes 1 second with Doppler effect. But when we do hydrogen and carbon, we have more lines, and it takes significantly more time to render them all because the accumulation is a very recursive process. But it is still able to render them. On the other hand, when we try to render the helium, for example, which has so many emission lines, and the galaxy is very dense, the renderer isn't able to render anymore unless we implement this merging algorithm with a very low tolerance, and then we can observe the results. In conclusion, we modeled Doppler effect and spectral volume rendering using a piecewise linear functions in real time. Our method is more accurate and efficient compared to the piecewise solution. However, it needs further optimization. And this can be accomplished using the large-scale data techniques available already in the literature. Thank you for your attention.